Lee. His first time in the festival. Hui is a theoretical astrophysicist. He did his PhD at Rice with Edison Liang, then was an Oppenheimer Fellow at Los Alamos and sort of stayed at Los Alamos ever since. In particular, worked closely with Sterling Colgate. Hui has worked on a variety of topics, including jets. He's well known for the great RFT in the sky approach to the subject, cosmic ray acceleration, reconnection, and angular momentum transport in disks, which is related to what he's going to talk about today.
Thank you, Pat. As Pat said, this is my first time here. I don't know how I missed it for the past 20 somewhat years. Although I guess I've never felt so warmly welcomed. So that's okay, that joke didn't go well. So, okay, I'm going to switch gears a little bit. This is astrophysics. So I was curious, has anyone heard of accretion disk in astrophysics? Oh, okay, better than I thought. Okay. I was asking Pat what topic to focus on, whether it should be disks or reconnection, MHD turbulence. In the end, we settled on the astrophysical disks. So I know we just had lunch and everybody's hot and so I kind of want everybody to relax and just ask questions as I go along, because I know this is something that you may or may not work on in your daily job. So treat it as a kind of a scientific American way of broaden some of the interests you might have. Of course, for students, I would love you to abandon plasma physics and come into astrophysics, as you will see that we're far more exciting. One thing is that you'll never be able to get in situ measurements, so you can use all your imagination as you want.
Theory always works.
Okay, so I'll briefly start with some introduction on the disk and particularly protoplanetary disk, and just think of this word as planet-forming disks, as planet formation is becoming one of the really booming astrophysical field, and there's a lot of work going into that. And then I want to specifically present to you two specific hydrodynamic instabilities. One is Rossby wave instability, and that will lead to vortex formation in such disks. And another is the we call spiral. I forgot the word spiral. Spiral. Okay. Oh, thank you. Okay, so observations, exoplanets. So this is as of 2 years ago. What's shown here on the horizontal axis is orbital periods of measured exoplanets. So Earth is here, in case you forgot, is 365 days here. That's one Earth mass. So it's a planet mass normalized by Earth mass. So all the solar planets except Mercury will be 88 days will be down there, slightly less than that. So you can see several populations. One, this is what we call hot Jupiter. Jupiter is 300 times the Earth's mass. So you have a population that's very massive, Jupiter masses, but there are day orbits. And this is the work that won a Nobel Prize a few years ago. Then you have also Jupiters at more normal distances, what we would call our Jupiter. And this is the region where the sensitivity runs out, so you can't see them. And we have another collection of planets that's what we call super Earths. So their mass is a factor of 10 bigger than Earth. So they're more Neptune mass, but they're closer. But presumably we're searching for Earth size down here and also at these distances for habitable zones. Now, so the bottom line message from this is that almost every sun-like star has planets. So rather than solar system being very unique, now almost every solar-like stars have planets. So consequently, we derive that this planet formation should be very robust, except we don't quite know how. So just very quickly, this is kind of an artistic view as supported by observation as to why how we think the planets form. You start with a dusty cloud of gas, dust that's measured, can be seen by Hubble, now can be seen by James Webb. There are maybe several hundred solar system in size, and then they collapse under self-gravity. And they, when they collapse, because they have finite angular momentum, so as they collapse, they start spinning up, so they form disk. And this is the disk lasts about a few million years. And then the gas and dust form into planets. In case you again forget what we're standing on, a dust. The whole Earth is made of essentially dust. A whole Earth's worth of dust. And then the dust and gas gets dispersed, and you were left with the modern day planetary system. So this is billions of years, and this is about a few million years. So if you approximate a central star and the surrounding gas and dust into a kind of a 1D looking structure. So you have as a function radius, this is Capillary rotation profile goes like 1/r to the half. Then because of the gas has a little bit of pressure, so it puffs up the disk. Otherwise, if the pressure is 0, the disk will be razor thin. But because of the gas has some finite temperature, so it puffs up the scale height a little bit. So you can convince yourself that the vertical component of the gravity would crush the disk to very small height. So h/r is on the order of sound speed over the Capillary V5. So that's a smallness parameter you want to keep in mind. That disks are usually thin. The thickness is determined by pressure. The pressure also, if you have a radial gradient, it modifies the rotation profile by usually deviating from the Capillarian on the order of h/r scale. So that's kind of the number sense you might have. So naively, if you take a rotation system like this, Lord Rayleigh back in 16 something or 15 something, I forgot, basically worked out that if you look at specific angular momentum of this kind of flow, it actually goes up, increases as a function radius. So that's if you exchange two fluids at different radii, it will restore itself back into this kind of shear flow, meaning they're very, very stable. So this problem that accretion disk with a nearly Capillarian profile is linearly, at least to axisymmetric modes, stable to the axisymmetric mode, has been a long-standing challenge in astrophysics for the past half century or more. Is how do you destabilize this kind of flow, causes mass still to go through the disk and end up on the sun. That's called the accretion problem. And one could say, oh, since you have a pressure gradient, maybe you could get radial convection by entropy gradient. That, for example, along this, the pressure along this profile has a gradient, or entropy has a gradient, and usually that also worked out. It's the epicyclic frequency kappa squared plus the Vasala frequency in the radial direction. And if you, because of the pressure is small compared to the V5 squared, and usually that number is also positive. So the disk is that stable for axisymmetric perturbations for Rayleigh criterion, as well as the radial convection by entropy gradient. So that has been the challenge for many years. As an illustrative example, our solar system, presumably the sun, all the planets are formed out of a gaseous dusty disk. So there's something called minimum mass solar nebula. This is kind of a very intuitive approach and say, what's the minimum mass you would need to form the star, to form all the planets. And the Jupiter, for example, is 1/1000th of the solar mass. There's a lot of gas in there. So you don't want to disperse gas too early before the Jupiter can form. And you can sum up all the planets in our solar system to figuring out what's the minimum amount of dust you would need in order to form all the planets. So you work through all those requirements, you actually come out with something like the surface density. This is because the disk is thin, you can, instead of doing volume density, you can integrate the height to get the surface density. Usually it goes like a radius to the -3/2, and temperature through fairly elaborate modeling, you can get R to the -1/2. And so you put in those numbers. So here I just took the standard solution. The gas goes is about this amount, and the dust is about 1/200th or 100th of the gas, and the ice, is also some form of dust. You can add up those two. So the usual parameter you can keep in mind is that if the gas were 1 and the dust is typically 100th of it, and that's the radial profile of the temperature density. And the temperature is pretty low; it's a few hundred Kelvin. So and at 1 AU it's a few hundred Kelvin. The further out is even colder. So you have all kinds of issues whether your disk can be fully ionized. Does MHD work, or do you stay with hydro, and all those issues. So this kind of disk you put in. Adding the linear theory machinery, it stays stable. So when you have a steady, stable, quasi-steady, stable, monotonic disk, we don't really expect any structures in the disk because you can do an experiment yourself. You have a strongly capillary shear flow. I've done this numerically. I just, really kick it and insert some structure into that capillary shear flow. Usually within a few shear rotation, all that feature gets sheared away. So it just shows how stable.
What do we mean for structure? Is homogeneity in the density?
I'll show you what do I mean by structure. So I mean, before all this, if you go ask an astrophysicist, when you observe a disk, do you expect to see anything? The answer usually means no. You're going to see just a smooth disk, because there's no instability involved to our knowledge for hydro. This is ALMA sub-millimeter array, and this is what they see. This is about 20 of them. Never mind those numbers. I never figure out how they name their disks, but you can see this one. You have rings, and then you have a little feature there, and there are gaps in the rings. So the bright color region, the strong dust emission, that means the dust and presumably gas somehow are concentrated in those rings. And this one also almost face on, you have all the rings. You can see rings in many sources. One of them shows a spiral if you really look, like there. And there's some with holes there. So how do you generate disks that's linearly stable to many of the known instability that we tried, and you can generate such really fancy structures? It's amazing that nature organizes disks. We're talking about 100 AU. So from the central star that's in the middle, tens of AU out to 100 AU, they form concentric rings. And they sometimes form blobs like that. They have spirals like that, and they have holes in the middle. It's just absolutely astounding. And out of those, they should all form planets. Like I mentioned, the exoplanet community told us every sun-like star has several planets. So we now have to use this kind of disk structure to understand planet formation.
So just to have a better understanding, at what scale is it the most difficult to produce? Because once you have a seed which is big enough, then probably you would say gravity kicks in and you see those structures, but it's probably the difficult one is to get into from very tiny grains to intermediate small clusters. Is that true or no?
Yeah, so if you put an Earth-sized object in the shear flow, it will be strong enough to perturb the structure to form, to even open gaps in some limit. So, but that's kind of cheating. Where did the Earth come from? So if you start with micron dust, which is where you bring in from the interstellar medium, this earlier, the dust in here is micron.
Is this first step, right, which is the most difficult, or is it true to think that?
I would say, so there are people working on cloud physics. They would consider their problem the most difficult and wonderful. You should work on that. There are people working on the disk, like me, and there's people work on exoplanets. Because by now there's no more disk, no dust and gas. You just look at individual planets. That's what JWST will measure the spectra. And they want to understand the structure, the mass of the exoplanet. So
this this famous Nice model developed by Morbidelli et al.
Yes.
At which position?
They're here.
Here.
Yeah. Well, they're a little bit of here and mostly here. Yeah.
So they cheat.
Well, it depends on where because it's not easy to arrange the solar planets. I mean, solar system planets like we have.
Yeah.
There are stability issues and why they stay that way and so on, all kinds of issues. Okay. Did I answer? Yeah, okay. So what I want to focus on today is mostly here and a little bit there. Okay. So I don't have a planets in the disk yet. I just have gas. There flows, but nonetheless, this is what we see. Why and how, right? So just to zoom in a little bit, there's really amazing multiple rings, like 5-6 rings there. You can look in detail. Maybe some regions are not as axisymmetric. And there's one source that just shows a gigantic vortex. That's, you can't even see the other side. Presumably they should be axisymmetric. And this one is also the red is the dust. And then you have this concentration, the big hole in the middle. And there's presumably some spiral structure. If you saturate the color, you can see the spiral also.
So here there is no sun.
There's always a star in the middle. Because this observation is in sub-millimeter, so they subtract the sun away in order to see the dust emission. Yeah.
What is the age of these things that we?
This one is young, it's less than 1 million years, which is a big puzzle also. This one even has a jet, has an infall, and all those things. Yeah, the disk shows very nice concentric rings. Some of this is a transition disk, maybe older. There's a big hole, so it's not one. So it ranges from less than 1 million years, maybe to 3 to 5 million years. Those ones could be towards the later stage of the planet formation. This one presumably is early.
How is that done?
They have the star measurements, and also they do class 0, 1, 2, 3 characterization based on the emission spectra. Yeah. And they then do statistically to get the age. The best known example is this is again the disk with a big hole, and that's the star. And they found that little thing there, and they zoom it in. They saw it's an actual planet. This is to my knowledge, the best known example where just to be sure, this, we don't know whether there are planets in them or not. We can't detect them, we just see the structure. And this one, we actually saw 2 planets. There's another one over here, but this one is much more easily seen. And this planet has 7 Jupiter mass. And the distance here is about 65 AU. So for some reason, heavy Jupiters form tens of AU away, and there's still gas dust around it, and we can see the emission from the equation. So the community is anxiously waiting for JWST this is one of their fixed target observation. So we're going to get some, one day you probably see news report than we do, earlier than we do. It's a very complicated system from the multi-physics standpoint, because as I mentioned, you have this young forming star that's emitting optical X-ray, infrared, and then you have a gas and dust disk that's surrounding it. It's being heated. So irradiation heating is in the outer parts of disk is the main way of heat the disk. And then when you have accretion going on, and you can viscously release gravitational energy that also heats the disk. That heating is mostly concentrated in the middle, in the near the star region, inner disk. And so there are lots of studies, very careful studies, look at ionization fraction, heating and cooling processes, and figuring out, so you write generalized Ohm's law, there's resistivity from charge neutral interaction and ohmic dissipation and ambipolar diffusion. This is Hall term. And there's also whether you have a magnetorotational instability in regions where it's highly ionized, which is over here, and in here it's not that much ionized. Here is you can be at a little bit more ionization. So there's wonderful topics like MRI, magnetorotational MHD turbulence, zonal flow generation, whether you have MHD winds. I would not talk about it today. This is a different topic. I want to focus on hydro here. Otherwise, we'll be here until tomorrow. Now that was dust. That was gas. Now it's dust. The dust particles. There's one thing I want to we all try to understand that the dust also feels the gravity. Okay. So the dust also goes around the star in capillary motion, because the dust particles don't have pressure. So they're individual particles, like little satellites, moving around the central star, where the gas feels the pressure. It usually moves slower than capillary. So the dust moves through this atmosphere, or not, gas, at a faster speed than the gas. So the dust particles always feel the headwind. It's a bit like on Monday or Tuesday, one of the talks was on droplets moving through the gas. I forgot, air maybe. Our dust is also, we characterize called the Stokes number, moves through the disk, because they always feel a drag, because they move faster than the gas. They lose momentum, and then they fall in. And one of the big challenge here is the dust, turns out they fall in much faster. The time scale is very short, like 10 to the 5 years. But since we're sitting on Earth, so something must have stopped their drifting. Otherwise, all the dust will be flashed out to the star too quickly.
Why you say that they move faster than the gas? How do you know? That's
so the dust particle move because there's no pressure among them.
okay.
So they move at Keplerian speed.
Okay.
The gas, which has a pressure, like I was saying earlier, usually pressure is high in the middle and low on side, so that's a negative number.
Okay.
So your rotation velocity is slightly less than the Keplerian velocity. So that's at the same radius. the dust moves at capillarian, the gas moves slightly subcapillarian, so dust always feels headwind. Then they lose angular momentum, and they head towards their star very quickly, which is another problem. I'm going to skip this. So it's a wonderful multi-scale issue. On the horizontal axis is the length scale, the size. Largest size, a few hundred AU, is what we see. The simulation can go down to, let's call it R. Simulation can go down to about here. So it's about 10 to the minus 3 R. So H is about 1% of R. So a fraction of H. So this is where the one simulation will be able to resolve, say a 2000 cubed. I don't know what's the largest plasma simulation. Anyone want to say? Let's say 2000 cubed. So in one big simulation in 3D, we can do 2000 cube simulation, resolving the full disk, resolving the scale height, and resolving about 1/10 of the scale height. But that's about it.
When you speak about simulation, you speak about particles simulation. With particles.
Gas plus particles.
Yeah, so gas on the
Two fluids.
plus particles. Okay.
Yeah, two fluid simulation. The challenge of this type of simulation is that you have to simulate for a long time because the disk has been going around and around and around. So it's a bit like the subarsenic flows in your machine when you simulate the whole device. I don't know whether it can do that yet. You have to simulate it for a long time. And then there's another approach says we're going to ignore the global dynamics. We're going to focus on between 1% to H, say. This is sometimes streaming stability of dust gets revealed the best, but they're in a very small local patch. They can't do the whole disk. And then we know the dust started at a micron, and they eventually become a mountain. St. Victoria's, right? So, I mean, literal, right? So the micron dust somehow all coagulate together and grew and become Earth and then become mountain. So that process started at a micron size, went all the way to hundreds of kilometers. And that's still long ways from the AU size that we're talking about. So you can't really have one simulation that captures all that. So what we do is like myself, I typically stay here and do subgrid modeling to study that process. Different people try different approaches, but that's where things stand. Okay, so I'm going to now discuss how we try to explain some of the structures. So I want to start with several smallest parameters to keep in mind. Because the intuition has to base on those numbers. First, we talk about the disk stays thin, so say 10% or 5% to 10%. The second, you might think about, you have so much dust and gas surrounding the star. How about the mass ratio between disk mass and star mass? So we call it mu. That's usually 10 to the minus 3 or 1%. So the precious little amount of gas and dust, that's all the reservoir you have for all the planets. So you want to keep them all, because otherwise, you can't form planets. It's about 10%, sorry, 1% to 0.1% of the star. Like Jupiter is 10 to the minus 3 of the sun. So that's this number. Okay. Then you say, okay, since you have dust and you're thin, maybe this self-gravity is important. So we have two parameters quantify the effects of self-gravity. One is we call G parameter, which is saying this small mass ratio, but let us boost it by the pressure effects, the scales square, and that number becomes 0.1 or 10. So it's because you say, what's this amount of gravity, even though it's small compared to the star, but maybe it's bigger than pressure. So you compare it to the pressure forces, you get about order unity now. So that means this cell gravity is actually being balanced by the gas pressure. There's another way of quantifying this, is the famous Tumori Q parameter. I wrote it in the same fashion. It's 1 over Q. Usually it's bigger than 1. It's it's 10 or 50. So this G is usually bigger than 1 over Q by a factor of 10. So the message is that we do need this mass to form planets, but this self-gravity could come into play because those numbers are on the order of unity, and those ratios can be bigger than unity. So the reason I emphasize self-gravity is because, as I mentioned, we see spirals, we see vortices, we see rings. We have to use some free energy to excite structures in such a shear flow because there's no other much energy available. So this self-gravity turns out can help us there. Okay, now I'm going to focus on vortices. So as I mentioned, if you look at a global disk structure, there is a region in our community we call it dead zone. This is because near the sun, the ionization is high because of the radiation, irradiation by the central star. Far away, the column depth is small, the cosmic rays will ionize it also. So both regions would have better ionization, so the coupling to magnetic fields are better, so the mass will accrete strongly. But this is the region where you don't get enough irradiation, the column depth is high enough, the cosmic ray ionization is not strong enough, that you have very little magnetic coupling, so the turbulence level is very, very low. So imagine you have mass accreting over here, and then there's not much mechanism to continue transport them, so they get piled up over this region. So this is very ideally, we approximate it as this is surface density, just have a bump. So this is what the dead zone might give you. Now, for those who work on fluids mechanics, the moment you see a bump in a smooth flow, even though it's strongly sheared by Keplerian, you say, aha, you might be able to do something when you have wiggles and profiles in rotation profile, in epicyclic frequency profile. So this is what we did years ago. Turns out also due to Lord Rayleigh, if you go to this book, I think it's page 81, if I'm not mistaken, there's a section, Rayleigh's inflection point theorem. If you have extreme in potential vorticity profile, like those kind of things, it's a necessary condition for exciting non-axis symmetric instabilities. It's not sufficient, but it's a necessary condition for that. And this is what's happened. So for the students among us, so I'm going to do something math very quickly. This is a 2D version of continuity equation, momentum equation, and equation of state. This is ideal gamma law. And then you perturb it, you choose some variable, you linearize this equation. You use eigenfunction f of r and e to m5 for non-axis symmetric modes. M is 1, 2, 3, 4, and you typically end up with a Schrodinger looking equation looking, and this is the potential, and that's the form. And you can see that you have delta omega. Sorry, I forgot to put down delta omega. Delta omega is omega minus M omega. That if that thing is 0, you have resonance, co-rotation resonances. And this F function is the limbless resonances. So what it's saying is that when this modified potential vorticity profile, potential vorticity is curl V divided by density, or in this case, density divided by curl V. Curl V is kappa squared divided by omega. So if you don't look at that, if you call that term 1, this is the vorticity divided by density. If that profile has inflection points, you have faster frequencies, you can get co-rotation resonances and limbless resonances. And if you do WKB approximation, you actually get this dispersion relation for those who work on Rossby waves, the drift waves. And this is almost exactly what you see, that it moves in the phi direction, even though the gradient is in the radial direction, but it drifts around the azimuthal direction. It has a deformation length scale on the order of h, and the instability comes from this term. So the physical picture is actually quite intuitive, and this is radius. This is that modified potential vorticity profile, that solid black line. And that forms a trapping region that Rossby waves exist between the inner limbless resonances, outer limbless resonances. There's co-rotation resonance in the middle. So the Rossby waves propagating, if it goes through the co-rotation resonances, we call over reflection. So the positive energy ones go through here. You only have negative energy Rossby waves. So there is a reflection of even more positive energy Rossby waves. So that Rossby wave gets amplified in this region. That's the instability. This potential well is not 100% infinite. So you have waves tunneling out of this trapping region. That becomes spiral density waves with positive energy and negative energy. And that's the over reflection of the Rossby waves by the co-rotation resonances drives the instability, amplifies it. And this is the eigenfunction I worked out a long time ago. And then indeed there is a threshold. The amplitude the bump amplitude has to be bigger than a certain number in order to excite that instability. And this is a mode structure, mode number. And this is what you will get nonlinearly. So you at the initial state, you actually have a density ring, density bump around it. That azimuthally symmetric bump, due to the Rossby instability, would then grow and break up into anticyclone vortices. And so those vortices then become great regions where dust will get trapped.
How robust is the bump? In other words, you make a maximum in PV that'll trigger an instability that's going to alter the PV profile.
Yes.
So the question for this to be at all interesting, you have to, in some sense, maintain the bump, don't you?
Yes.
Which must be maintained by the absence of accretion. It's the dead
Actually,
spot.
by not absence.
Accretion to the point of where you hit the dead spot.
Exactly.
Yeah.
So long as you have, I will show a movie of that. We actually simulated that situation where when you have continuous matter coming in, it will necessarily grow that bump.
But then you have to explain what's the accretion mechanism, which you sort of dodged that so far in the talk.
I will dodge it towards the end because usually people would use MRI or MHD winds here. That would drive it. So I kind of work in the limit where for this talk, where the sun is already formed and you have 10⁻³ or 10⁻² of mass and gas and dust here. And then you ask the question, can you form structures? there is still a amount of accretion going on facilitated by those processes. But those processes, no matter what they are, they cannot destroy they can help you form the structures, but they cannot destroy them because we see them, right? So that's the logic here that this, because the star is already formed, you're not relying on a huge amount of accretion rate to supply the mass of the central star. I mean, just to give you an
You
example.
say that's a sufficient accretion rate to maintain the bump.
Yeah, so the typical observed accretion rate here is on the order of 10 to minus 8, minus 9. So in a million years, it's only 1% of the solar mass. The sun, is one solar mass. So in the early stage, that's a different story. Then you need 10 to minus 3 or 10 to minus 5 or 10 to minus 6 solar mass per year so that you can form the star less than a million years. Yeah.
And densities of the bump in gas or in dust or both.
It started presumably because remember the dust is only 1% of gas mass. So the mass is dominated by gas. So you have to work with the gas first, the dust will follow. And later I will show when the dust gets more concentrated, it becomes the dominant driver. And then you generate even new phenomena from that, which is observed now. So this is the theme of the conference. You have feedback.
This is where it's not ionized.
That is only where the ionization is very, very low. Yeah.
So you have to assume, which is probably what Pat's saying. I mean, really, you've got to think of the whole disk, and the fact that it's not ionized somewhere means that, even if you did a linear stability problem, you've got it ionized somewhere, not ionized somewhere. And you're looking at this as a sort of local problem, where you're saying.
This is actually maybe 10 AU. Yeah, local in that sense.
10
Yeah,
AU,
yeah.
Depends how many AU this guy is.
100.
Okay, but I mean, it's like if you take, if you do a shear flow, for example, and it's unstable, you might say it's stable, somewhere unstable, somewhere, but you have to do the whole eigenvalue problem, and then it will be unstable. So you've got a reason for thinking that you can just look at the dead zone without bothering the rest, which is presumably this.
No, so in a way, this region, we have accretion. And so is that region. It's just m dot may not be, in order to try to maintain the same m dot throughout the radius, something has to happen over here. Does that make sense?
Let's try it in a different, I like to think in terms of alpha rather than m dot. What alphas do you need, inner and outer?
So you can use the usual alpha, say 1% here.
You need 1% to make this story fly, as you're saying.
Not my story, the accretion usually requires.
No, I know, but I'm
yeah.
talking about this. How much alpha do you need to feed and maintain the bump?
So the outside is alpha is 1%, the inside is 10 to minus 4. Yeah.
1%.
Yeah. Okay, so now this is what would happen to the gas, that it will break up into the vortices, and then now you add dust to it. I didn't explain the vortices are actually anticyclone. There's a reason for it, because if it's a cyclone, it gets sheared away by the background shear motion, because the whole disk is going this way and the vortice is going that way. And they're limited in radial extent by the shear flow, and they can be elongated in this direction. So that's the feature of Rossby vortices in such flows. So to do dust two fluids, I just grab some of the equations from the paper. We can do it in 2D and 3D. And the key terms here is actually the drag forces between the dust motion and the gas motion. So the dust is leading the gas, so that's a negative sign. This is drag on the gas, and then the drag on the dust, and then this motion is the speeding up of the gas. So those are the terms that the interplay between the two. Let me skip that. So this is kind of a setup, right? Back to Pat was asking, or David. So this is radius, this is 3D phi, and then there's a azimuthal direction. This is Z. And this is kind of the dead zone region we carved out for the alpha. So in this particular situation, this is about 10 to the minus 4. And this saturated maybe go up to close to 10 to the minus 2. This is kind of your direct answer. And then we let it go. And we let it accrete also from the top through the mid plane. And then this region, you're going to have a density pair up and then see what happens. Okay. This movie is a mid-plane cut of that 3D run. Notice this is already a long time ago. So you take a long time to set up the accretion flow, but once you get it going, what's showing is the density. So you get a density bump that breaks up into this elongated vortices, and then vortices transport and momentum very efficiently, and then it smooths out, become a ring again, and then it waits for the more matter accretes, and then it triggers the Rossby wave instability again and becomes vortices. So there are several cycles going on there. Okay. Okay. This is another type of simulation where we want to study the trapping of the dust inside the vortex. And this is the gap. Now, this is radius. This is phi 0 to 2 pi squashed in the direction. So it looks wrong, but really it's elongated because this should be multiplied by the 2 pi should be a lot bigger. And you can see that the dust, this is the gas, this is dust, and then the dust all drifts toward the center of the vortex. And in there, this color means the dust density is higher, is equal to the gas density. When it's go above 1, the feedback actually can destroy the center of the gas vortex. And because their motion is different from the gas and it's faster. So there's kind of a hint of a new type of instability occurring within that vortex. And we didn't quite work out a linear theory for this. Yeah.
Maybe I'm missing something, but are you saying that when you have this Keplerian profile, it's very hard to get structure? So you will get structure in the dead zone. So is it right to think of it that, across this 100 AUs, you will first get structure in the dead zone, and afterwards you showed all those very complex features which extend over the whole length, the whole radius. So at some point you generate in the dead zone, and then you expel those things and you keep producing them in the dead zone. Is that the mechanism? Or?
The second part of the talk, I will talk about ring formation, and that explains, at least as far as we're concerned, more the global ring structure. I choose this one to go first because the Rossby waves, maybe you all know, and this will be specifically for those regions where you see vortices. So this cannot explain the whole multi-structure. We have to, I kind of bring the problem, chop it into pieces. So if you ask, how do you construct the global disk model? I have to talk about the ring part first. And they form rings. And then if you get planet form, the planet would generate vortices also much more easily for you. So we don't, at the moment, the community doesn't really know who comes first. Is it the structure come first, then planets, or the planet first and then structure second? There are different arguments, different models for which. I tend to stay in the camp of let's work on structure first, the planet second. But that doesn't mean that's true. The other models somehow would put in the planets, and the planets would generate all kinds of structure for you because it's so massive, it perturb gravitationally the disk strong enough that you can generate many features.
Can I ask how much the two fluids approach is realistic in presence of dust? I mean, you might have caustics and situations where you do not have a well-defined velocity field at any position inside your disk, right?
So the mean
for the heavy particles.
Yeah, the two fluids modeling relies on the Stokes number of the particle. So as you calculate from micron to say 10 centimeter, and then beyond that, you can't treat it as fluids anymore. They become bodies. 10 centimeter, that's a rock you can barely hold in your hand. I mean, loose rock. So mean free path of those particles between micron to millimeter, centimeter is still very short. So we treat them as a drag. Now, the next question is, are the background disk flow turbulent or not? This is where different models start saying different things, right? If you have strong turbulence in the background flow, how would you treat a particle by a drag or by some other process? Should it be Brownian? Should it be super diffusion? I mean, this just become very difficult. So the community parameterize that process using different ways. Now, the observational test of it is to say, if you start with micron dust and they drift and they coagulate and fragment, and then spatial distribution for different sizes will evolve. And then observationally, you can go a factor of 10 or 100 in wavelengths. Then that will be sensitive to different sizes of dust. And then you can test some of the global models, whether micron size should stay outside, the centimeter should go in, millimeter will be halfway, and so on. So there's global tests like that to constrain the model somewhat.
Do we understand your color picture that the PV is homogenized in the vortex?
Yes.
Okay, that at least is doing what it should.
So the referee would say, why bother with this quantity? I said, well, there is a whole plasma community who wants to see PV or atmospheric science.
It's a check.
Yeah.
Why isn't the dust homogenized as a scalar?
Because, okay, if you go to a particular fixed region, okay, and you ask yourself, who is the momentum driver? It's the total mass times its velocity, right? So when the dust becomes more and more massive in that region, have more dust than the gas, and it moves at a Keplerian velocity or some circular velocity, it becomes the momentum driver. It tells the gas to follow them, now the dust follow gas. So that's where the feedback becomes very important. Eventually, even shred off the gas vortex. So, but astrophysically, what I did in the paper is to say, oh, how much mass is there? It's 10 Earth mass. So presumably they've now quickly coagulated and become big rocks. They should drop out of my two fluid simulation and start forming planetesimal on its way to form planets. So we don't have that closure in it. So a leakage of the gas of the mass. So so you have to take this with a grain of salt. That when the feedback become very strong, other ways of draining the gas dust away.
Is a distribution in size and mass, by the way, or is it just that because of this mechanism, it's kind of unique?
If you look at Stokes number, which is the way we calibrate the size of dust, for small Stokes number limit, they go with the flow. The velocity difference between the gas and dust is tiny. Somewhere around for the typical protoplanetary disk, somewhere around a millimeter is when the different velocities become very, very strong. And that's where you see a lot of drag going on. So, but we know by observing at different frequency, the dust grew to that size, because otherwise you wouldn't scatter the light at a millimeter. So that's a wonderful confirmation that dust has to grow. Now, the growth process and the fragmentation is not a whole big kind of worm that we have models for it, but it's not well tested. Some of our work actually, this heroic subgrid modeling, in all the hydro simulation, each cell, we also evolve the size by subcycle it. So you start with some delta function and it fills up the whole size bin. That takes a long time. Okay, I think probably. So summary on this part, the potential releaser profile, kinetic site, vortices, and they then trap dust and likely sites for planet formation. Okay, let me quickly, I think I run out all my time, right?
You'll be getting a lot of questions.
Okay, so I'm going to talk about rings. This is actually even more fascinating. Let's skip this. Okay. So again, it looks very innocent, right? You take 2D continuity equation, momentum equation, self-gravity, and adiabatic equation of state. Then what you want to say is okay, because we're looking for spirals, right? So, and we say, let's just take m equals 1. But we make the approximation that we are looking for a very long period, very slow modes, because astrophysically, when you see something in the sky, it cannot be too dynamic because human life or the rotation is too short. I mean, it takes a few years, but this thing has been sitting there for a million years. So you naturally want to go with, let's first do the low frequency limit. And instead of the usual density, velocity, and pressure variation, let's deal with eccentricity, because we are looking for spiral features, which is eccentric. So this is all worked out back in the 90s to say, what if we perturb this equation using eccentricity as a variable, and has a very low frequency limit, assumes m equals 1, and you get this big equation. This is not new. This is not our work. This is actually work done much earlier, but this person really did very well. He unfortunately left the field. So what it says is that the eccentricity of any modes with low frequency can be driven by the pressure gradient effects and also self-gravity effects. So, okay, now if you don't like my density bump, I'm going to take a monotonic. This is just some feature, don't worry about it. This sigma density and then rolls over. This rolls over is observationally true, because this cannot go on forever. It has to stop. So this rolls over, and the temperature, if it stays as a single parallel, T to the minus R to the 1/2, yeah. This G parameter that I was talking about actually has a peak. Okay, because of this self-gravity compared to pressure. This is where things get very interesting. This naturally rolls over of the density, and the temperature stays quasi following the parallel because it's done by heating, by the cosmic ray heating and the other heating. It would create a non-monotonic profile in G. And because of this structure, it turns out you actually get 3 different kinds of modes, which is illustrated here. One is just elliptical pressure modes, just that G traps it, and you just have eccentric rings. Another one is you have a mixture of pressure and self-gravity effects, and you can see it. There are concentrations arise because of the self-gravity. The third one is spiral modes when the self-gravity is strongest, so that you actually get the spirals. You started here and swirling out. And if you work out the WKB approximation as a functional radius, you have what they call Q barrier that traps the spiral modes up here, and then the limbolet resonances would trap the pressure modes down over here. So this was understood back in 2019 that when you have profiles like this, because the G actually has a trapping, that you can sustain those 3 modes. We look at it and says, let's see if we can make it unstable. Long story short, they are. The spiral modes can be unstable. So we actually tried this kind of profile, like the paper head, and the G goes, the magenta curve goes like that. We also tried the discs that had a big hole in the middle, like those kind, and also rolls over. And the G would almost follow the sigma profile because the CS square is slowly varying. So the bottom line is, so long as the G profile has a peak and has a broad width, and the peak is high enough, and those kind of disc profiles would trap eccentric pressure modes and the spiral modes. And spiral modes under self-gravity become unstable. So what we did is to say, okay, let's be more general in the equation of state. This is entropy. You perturb the entropy and let it settle back in with some cooling timescale, settle back to an equilibrium temperature profile. And then we can normalize this cooling time either by a beta constant, either it's adiabatic when it's infinite, or as beta is 0, is isothermal. You just keep locally isothermal, you keep the temperature profile. And you can do the same thing. You look for eccentricity perturbation. We now, instead of 1 term, we got 4 terms out, right? So there is adiabatic response of the pressure, isothermal response of the pressure, this self-gravity, and if the beta cooling actually has a radial dependence. And this is a huge equation you have to solve. But the bottom line, without going over all the details, the frequency versus radius, you have the usual limbolet resonances, but then you also have this self-gravity trap within the G profile. The spiral waves become destabilized. So this omega actually now grows a positive imaginary part.
And when you bring the cooling, does the self-gravity become the dominant driver of the eccentricity node?
So this orange peak disappears when you go to adiabatic. Yeah.
So the answer is yes.
Yeah. You need fast cooling. Isothermal is kind of fastest you can get, but somewhere between these two, in the paper, we'll go through the details of the boundary separating all this limit. Yeah. Yeah.
How do you understand physically this G term? Because it's a ratio of reduced mass over some
Pressure. Yeah. So there's, well, physically, it's just the gravity will try to collapse a gas cloud, right? Because they will keep getting smaller, smaller, denser. The pressure would fight against it. But there are different ways of writing that ratio. So this is what I was talking about, the G and the Q. So the tumor wrote it in such a way that had a rotation in it, so that he had the tumor Q parameters c times kappa, sound speed times kappa divided by self-gravity. So I guess in a way his is a mixture of pressure and rotation, whereas this G, you just a straight pi sigma G divided by times R times sound speed. There's no rotation times pressure downstairs. There's no rotation involved, but those two are related in the disk formulation. So I don't have another way of separating the two other than it's always some sort of self-gravity over pressure, but they're not the same.
No, but in tumor is a fight between self-gravity and differential rotation at large scales, which is the kappa squared,
Yeah.
right? And pressure at small scales, which is the usual G's thing.
It has a C in it.
That's pressure.
Yeah.
Okay, so the question is, how is this eccentricity story different?
Oh, because the this is the tumor parameter.
Right,
It's bigger than 2, so it's stable.
right.
Yeah. So you look at this tumor. I mean, indeed, we show the tumor would not drive any instability.
Well, it depends
Yeah.
on your sigma, it depends on the surface density, right? If you have enough surface density, it can drive, and then
Yeah.
Off you go, right?
Yes. So we work in the parameter space where tumor is stable,
Okay,
but G is big enough that it's destabilizes the spiral modes.
but it's this eccentricity spiral mode.
That's
Yeah, but
right.
the question is, how does this get around the constraints of tumor? And tumor is very easy to understand what's going on. Like you have self-gravity, and on large scales, you have differential rotation. On small scales, you have pressure. What's different in the eccentricity mode?
It has to deal with the thermal physics.
With-
Thermal physics,
Right?
because the thermal
So
gradient
you've got
actually.
tumor in your little box there. So
Yeah.
what would be different for the eccentricity mode?
First of all, this is M equals 0.
Right.
Yeah.
But I mean, even if it, even for tight winding and M not equals 0, it just becomes little omega minus M times rotation squared on the left-hand side.
Yes.
Right.
So that's I skipped this slide, but you want to talk about it, yeah. So
Well, I'm
that's
just trying to understand, seems like the eccentricity mode is getting around some basic constraints here, and I don't understand how.
Well, this is so the way I look at it is that its tumor is stable for the axisymmetric perturbation.
Right.
But as you go to the eccentric mode, where especially the spiral mode, which is the next slide. So Kim, this is the tumor Q. Oops. I mean, this should really be kappa, but usually for Christian disk, kappa and omega are essentially the same. But the G is, there's no rotation involved.
Is the eccentricity mode simply a non-axisymmetric spiral density wave?
No.
No.
It has the.
I mean, you've got all this song and dance, with the propagation between the Lindblads and the different, negative energy wave feedbacks and blah, 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 and spiral density waves again. So, I mean, and again, what's special about this eccentricity thing?
It's being trapped is what, because without the G, if the G is too I mean, if the profile, if the sigma keeps on going, you will not trap those modes at all. Those modes don't get excited at all.
So you wouldn't get them in your garden variety galactic disk, would you?
If your G profile doesn't have this
It
trapping.
doesn't have the right profile.
Yeah.
Okay.
So this is in a way very new modes when you have this kind of structure.
Right. Okay.
Yeah.
It's unique to this set of profiles.
Yes,
Okay.
yeah. It's not a garden variety generic smooth disk, monotonic disk.
Yeah. Yeah. Okay.
We already kind of mentioned this, the brochure. So this is what happened. You can see the spiral modes grow, be destabilized. This is sigma. This is the mode 1, m equals 1. And you start seeing the ring appearing. And then you get another episode of spiral mode destabilizing, and then it saturates, and then it gradually evolves into multiple rings again, and you have to wait for a while. So this is, as far as I know, you know, the mechanism where you can, depending on where you capture the disk, you can also see the spiral, but you can also wait long enough that the spiral would saturate, ultimately transfers angular momentum to the background disk so that m equals 0 mode becomes the dominant one. And you take a picture of the disk and it become a multiple ring signature. Okay. So this is the mode growth. It started with small amplitude, exponential growth. This is stage 1. And then it saturates. Actually, you can see a small, another growth, and then gradually saturates and dies away. Now, this is as a function radius, the surface density average. And initially you have the smooth profile. And then so you started at this blue is early time, yellow is late time. You can see the surface density start showing multiple peaks, 1, 2, 3, 4, 5, possibly 6 peaks. And that's how we think the multiple rings can be generated. Now you ask what's actually happening in terms of angular momentum. So for eccentric modes, because of the eccentricity, it's if you imagine an eccentric ring, it actually compared to the Keplerian ring, the circular ring, it has a smaller angular momentum, because you know if E is small, you expand this, but if E is 0, you get back to the Keplerian, but if E is smaller, E is finite, so you get a smaller. The eccentric ring has a smaller angular momentum than the circular ring. Okay. So as you grow the eccentric modes, and then you can calculate the angular momentum deficit, integrate, you know, as a find the time derivative, you actually see this growth effect. And because eccentricity grows like this kind of growth rate, this is the G. So as the eccentric modes continue to grow, it gets, this energy gets smaller, and this angular momentum gets smaller and smaller. The angular momentum then gets shared with the background mean disk profile. Because this mode, the eccentric mode has a different spatial structure, has a specific angular function spatial structure. That's how it picks out certain regions deposit the angular momentum to the m equals 0 background state, and that grows the m dot picture comes in and grows.
So does it conveniently work out that more of the angular momentum goes to larger radii?
It's not necessarily large radii, it's at a specific
So, I
location.
mean, the
Yeah.
question is, if you want to accrete, you have to have a flux of angular momentum outward, right? And otherwise you have a little problem, so.
Yeah, but remember the G peaks, well, in this case, it peaks around here, but usually it peaks at a more towards the outer.
Mhm.
And so then it generates rings. So that deposits the angular momentum at a different location that way.
Well, the issue for angular momentum is true for the dust, not for the gas, right?
No, this is all gas.
Uh-huh.
This is what's amazing, and what I found amazing is that because of this looks innocently looking bump at some larger radius, and it traps the elliptical modes and particularly spiral modes under certain condition. It destabilizes it such that the mode structure across this whole disk deposits angular momentum at some specific location. And I mean, gives angular momentum to the background state, and that causes accretion in such a way that you made those multiple bumps. That's how the rings gets generated in gas. And the dust then just simply follow this because it's only 1% of mass to begin with. Yeah.
So, and whereby do you get this profile in real life? Is it because to a boundary condition effect, basically, you don't have a perfect symmetric due to what happens very far away, or you have a binary star, or you have something which is non-symmetric somewhere?
So initially everything's symmetric.
Yeah. How do you get this asymmetry?
How do I get which asymmetry?
How do you get that specific form of G, which
Oh.
is reminiscent of an asymmetry somewhere?
Because the sigma has to cut off. If this goes like r to the -3/2, you integrate over the whole disk mass, it has to stop somewhere, because otherwise it's infinite. So that we know observationally disk cannot be too big. So this rollover has to happen. Now you can do the more detailed modeling, see the blue line, whether the temperature stays high or whether temperature also drops. But usually, because here at outer disk, the temperature is heated by cosmic rays and all that. So the temperature drops a lot smaller, slower than the density. So you almost always get a bump. Yeah. So this is astrophysically motivated, I would say. But what's new about this work is that it turns out that bump can trap modes, new modes, and under some conditions destabilize them even. Yeah. And the nonlinear consequences, multiple ring formation. Maybe I should skip this. Maybe just asking some questions. Let me just close it. And I had another topic, but it's getting late. So what we're aiming towards, which I didn't talk about, is this 1% of H streaming instability. And then in global 3D, there's Rossby wave instability, there's vertical shear instability looking at sideways. So what we're now gearing towards is combining all three, both for gas and dust. And we're computationally we're getting there. So for example, this is a 3D disk with gas and dust, and that's the simulation size. We can see the vortex formation, the dust concentration, and then vertically we can see the vertical shear instability. So in this run, Rossby wave, streaming instability, and we need extremely high resolution for it, but we can do it. And then vertical shear instability, all three are combined in such one simulation. So we can see the lots of, this is log scale, the dust density clumps forming due to streaming instability. And then the big vortex also concentrating dust inside at the boundary, there's also streaming instability forming. So it's there. So to summarize, I think observationally, it's far more rich, surprising than we initially thought. Vortices, rings, spirals, and big holes. There is still debate going on whether we should do everything MHD or there is room for hydro. And for this talk, I stay with hydro, particularly two instabilities. One is Rossby at the edge of that zone, and also new spiral eccentric in a self-gravitating rapidly cooling disk. And the second one particularly is naturally leading to multiple ring formation. And this one is naturally leading to vortice formation, all of which would trap dust around them. I think future we'll be able to combine those in 3D and be able to investigate streaming stability, vertical shearing stability. Those two I did not talk about, and Rossby, as well as this new eccentric spiral eccentric instability, and see consequently what are the conditions that would be suitable for planet formation. Thank you.
More questions, anyone?
I have a question. I feel like you assume it was fluid, but you neglect, for example, at the beginning of the gas, you neglect the viscosity. So how do you thermalize your system, and why do you don't take a directly kinetic approach, like the Glasgow approach?
So if you look at the mean free path of any collisions, that's much smaller than the scales we see. So often we treat them as fluids, unless you go to some of the top layers.
I'm asking that because I've seen some plasma today where like you have holes also, and you just know that the plasma passing style of this, depending on your initial condition, you relax the state where you have those.
But yeah, but the collisions are very important. So it's yeah. But you're thinking about treating the dust part or treating the gas part?
I don't know.
Yeah. Yeah, for the gas part, usually the fluids it's pretty good.
So this dust is treated as a particle, or?
It's our codes are two fluids. So there is a gaseous fluid and there's a dusty fluid, and then they couple through drags. And then the Stokes number for different size being with it. There are other numerical treatment would have pseudo particle treatment, just like in fusion, there's also the particle method versus the fluids method.
So this dust where you were talking about ionizations like cosmic as well as solar. Dust particles there are charged?
Yes, so that's another level of complication that we're not handling. The dust evolution inside the disk, there's also chemistry going on, there's different ice lines, ionization, and there's a whole zoo of processes.
That may not be Newtonian fluid then.
That's right. So yeah, I don't know how to do those things.
Well, seems
It's a short one. In the last part of your talk, what determines the number of the rings? Is it related to the boundary conditions, or?
The short answer is I don't know the answer to that question. We've thought about it for a long time. It has something to do with the spiral wave structure. Because you have a G profile, you trap the waves bouncing between the two. And sometimes it's standing wave structure and you have nodes. And then the angular momentum exchange between that spiral mode and background has specific locations. So that it's not a uniformly changing angular momentum. So we calculate all that. But we don't have a way of saying, oh, looks like a 3 or that looks like a 5. And we can get anywhere between 3 and 6. And they also move. So because what's happening is as the mode exchange angular momentum with the background, excite M equals 0 mode, that changes the G profile. Remember, the G takes the sigma. So as you evolve, the G changes, and then there's no way for us to track anymore. But nonlinearly, we see another wave of generation because the G got changed. So in the end, we've never seen it less than 2. It's always 3 or above. But we don't have a first principle way of answering how many we should expect.
And the change in G, by the way, just is moving to saturate. Is the reason for nonlinear saturation?
Yes.
All right, Chris, we go around you later. So Chris, and then we'll have a second pass. So Chris now.
I'm sorry, maybe I lost the thread along the way, but I mean, just maybe kind of thinking ahead, you mentioned, this is all in the hydrodynamic thing leading out all the MHD fund. But have you thought at all, if you did include sort of any like MHD coupling the field aspect, how would that impact the elliptic sensibility? Sense of what might change, what we expect to be, or maybe like the G small parameter would even really matter?
The G profile, even for MHD models, would still say G profile is like that because, like I argue, the sigma has to roll over much faster. In fact, there's even observationally data points because they're so large they can see it. So the G profile will be there. Now, whether the MHD stresses would change the pressure. So the trapping really has 2 terms. One is the pressure gradient, all the terms in there, and the self-gravity. So you now have to add a magnetic stress term. And whether that would kill the driver, so we don't know. So partly we thought about it but didn't do anything is because if we say what B field should we put in and configuration should be there, and is it turbulent, and we don't have a good answer on those, so then it's hard to formulate their stresses. So I guess in a way we could just thinking out loud, we can take the MRI turbulent stresses and parameterize in some way, and then see if we kind of stabilize the modes or not. Yeah.
We have one over here.
Can you explain, please, what is the main difference between gas and dust in a mathematical point of view?
The dust do not have pressure. They're individual particles. The gas has pressure. Like this room, the gas has pressure, but if the dust storm came in, the dust particle will move. They don't feel each other. They only feel each other through gravity. So you can think of dust particles as many particle satellites that they don't have pressure forces. So then, and there is a central gravitational sun. So the dust would travel at a Keplerian speed around the sun, or with some eccentricity. But the gas, because there's pressure, so they typically move at a slower speed than the dust. So that's usually how we think of them. Is that what you're asking, or?
So we can go back over here now. Well, okay, well, you and then you. All right, go ahead.
So when you are doing a planet also has also moons, so does it work? Can you scale to when the formation of moon around Jupiter? Would it work?
So the vortex picture I show, the results there, one of the thinking is when you form a vortex, it stops the other dust. Let's say you are the sun, I'm the vortex, and this is some outer region. The dust is all drifting in. Once I have a vortex, I'm sucking out the dust. You know, there's no more dust passing me. I mean, I'm a great vacuum cleaner. But I will first form a Jupiter because they condensate, and then I'm still here, so I'm still stopping all the dust drift. So it promotes new generation of planet formation. So that's an idea. I don't think anyone has worked out the details as to the sequences of the next generation of planet formation. But it offers hope in that sense.
Right, yeah.
You have this density bump in the dead zone, hence you have the Rossby waves. Something I've not spoken the name of is zonal flows. And you can, well, one could easily think that with all those Rossby waves going on, the zonal flows that you would generate would spare out any kind of structure that starts to occur, or if it becomes cardinal unstable, could feed back or generate further structure. So what's your take on that? Or zonal flows or stuff?
Yeah. We don't have turbulence in the hydro in this. So but I didn't show. We've done 3D Rossby vortice simulation. So there is a interesting question is you do 2D, you form a anticyclone vortex, but you do 3D. Let's say you go up, they're strongly stratified. So Varsala frequency in the vertical motion is actually short. I mean, it's 0 at the midplane, but very big at a one scale height up. Would it behave like a Taylor column, or would it have different shear, and that would destroy the vortex? So that's one issue. What you talked about is to say, what if there's a turbulence background that would spontaneously generate zonal flow?
Necessarily with turbulence. Just the fact that you have Rossby waves and that density.
Just the self-interaction of the Rossby wave, you should get his own.
But you need a full spectrum of Ks.
Not necessarily, no.
Just 1K?
Yeah.
Oh. Okay.
Question, I think he's asking, the question is, this thing ought to have an effect on the bump, right? I mean, we in our business, we talk about zonal flows and zonal corrugations. The bump could be due to a zonal corrugation, right? The density modulation associated with the zonal flow.
That I've not thought about. Yeah, maybe I should learn more as to how.
That's been seen. I mean, some of these simulations by Uden and his,
Yeah,
Clar and all,
Yeah.
definitely have seen zonal flows. I mean, they're doing MRI simulations. So they're
yeah. The
not
MRI
this
is
stuff.
easier. Yeah, so I always associate zonal flow with turbulence, but maybe.
MRI isn't easier because you have the magnetic stresses.
No, sorry, easier in terms of maybe generating zonal flows. Yeah,
Okay.
but I'm not saying the work is easier.
No, I mean, it may not. I think it's easier without magnetics to get them. I would disagree. Sorry.
I would love to see it happen. I should learn how to set up the problem.
Anything else, or can maybe continue the vortex over coffee? So let's thank Hui again.
Thank you.